Hey there, it's Shannon Magic Myers, and today we'll be really quickly going over Lagrange multipliers. So basically, evil plan is we want to be able to understand the method of Lagrange multipliers and then use these multipliers to solve constrained optimization problems. So it turns out that many optimization problems have restrictions or constraints. On the values that can be used to produce the optimal solution. So, Lagrange's theorem, let f and g have continuous first partial derivatives such that f has an extremum at a point x0, y0 on the smooth constraint curve g of xy equals c. If del g at x0, y0 is not the zero vector, then there is a real number lambda such that del f of x and y is equal to lambda times del g of x and y. All right, so the method. Let f and g satisfy the hypothesis of Lagrange's theorem, and let f have a minimum or maximum subject to the constraint g of xy is c. To find the minimum or maximum of f, use these steps. And sorry, there's a couple of typos in here. So first off, simultaneously solve the equations del f at x and y is equal to lambda times del g at x and y, and g at x and y is equal to c by solving the system of equations fx at x and y is equal to lambda times gx at x and y, fy at x and y is equal to lambda times gy at x and y, and then g at x and y is equal to c. So then you evaluate f at each solution point obtained in this first step. The greatest value yields the maximum of f subject to the constraint g at x and y is c, and the least value yields the minimum of f subject to the constraint g of xy is c. So this first example, I want to make it a little less trivial, so we're doing a different one. This f at x and y is equal to e to the xy, and our constraint is going to be the circle x squared plus y squared is equal to 8. So the radius will be root 8, which is between 2 and 3. So basically, what does this mean? This means that when we're optimizing f, what we have to do is keep in account that the values have to be within this circle, okay? Because x squared plus y squared is 8. All right, so that's our constraint curve. Okay, so here we go. Let's check it out. Another thing, we are also assuming that x and y are positive, so we'll need that when we are solving. So what is our constraint? Our constraint is that x squared plus y squared is equal to 8. And remember that we want to solve our system del f at x and y is equal to lambda times del g at x and y. And then we also want to include with that our g of x and y, so this is just in general, is equal to c. Cool so far? All right, so here we go. Let's see what we have going on. So our g of x and y is equal to x squared plus y squared. And again, remember that that in turn has to be equal to 8. So, looking at our system, fx at x and y equal to lambda times gx at x and y is going to give us what? Beautiful. We will get y e to the xy is equal to lambda times, good, 2x fy at x and y will be equal to lambda times gy at x and y. And so we would get this time x e to the xy is equal to lambda times 2y. And then remember, we are still looking at our constraint, which is x squared plus y squared is equal to 8. So putting this all together, let's see what we have going on. If we were to isolate lambda on each of the equations that have lambda, what would we get? Well, we would get from this one, lambda would equal to y e to the xy over 2x. And from this one, lambda would equal to x e to the xy over 2y. So you can either see by inspection that that y has to equal x, or you can set these two equations equal to each other because they both equal to lambda. And so we would get y e to the xy over 2x is equal to x e to the xy over 2y, which would yield 2y squared e to the xy is equal to 2x squared e to the xy. Dividing out the 2, we would just have y squared e to the xy is equal to x squared e to the xy. So therefore, do you see that y squared must be equal to x squared? And so y would equal to plus or minus x, but x is positive. We'll say that y is equal to x. Cool, cool? Okay, so now working with connecting these two here, all right, what we will have is x squared plus x squared would have to be 8, and that's because y is equal to x. So that gives us 2x squared has to be 8. X squared is 4. So x would be plus or minus 2, but again, we throw out the negative since we were given in the problem that x and y are positive. So x is 2, which means that y is 2 since x equals y. And what will happen is f at 2, 2 will be and I'm sorry, this actually, my bad. We're maximizing this. Forgot to change that part too. Maximizing. So f at 2, 2, which would equal to e raised to the 2 times 2, which is e to the 4, is going to be the maximum taking into account this constraint. Cool, cool? Okay. Now, this problem here, don't worry, it's all good. No changes. We want to use Lagrange multipliers to find the minimum distance from the curve y equals x squared to the point -3, 0. So now we have to come up, we've been, actually it's a little sneaky, we've been given our constraint. And how do I know this? I know this because we are minimizing the distance from that curve to the point. And so our f of x and y what we'll do is we're going to do work with the square of the distance. So we can let f be the square of the distance. And it's, of course, the square of the distance between y equal x squared and the point 3, 0. So f of x and y is going to equal to, well, we're working with the point -3, 0, right? So we'd have x minus -3 using our distance formula, quantity squared, and then plus y minus 0 quantity squared. So f at x and y is equal to x plus 3 squared plus y squared. And so at the end of the day, we're going to have to square root whatever function value we get. Now, our constraint is y equals x squared. Well, now we can just subtract the x squared and say that y minus x squared equals 0, so we have our c, and then we don't get confused about that. So, finding all of the pieces, right? Because remember, at the end of the day, you want del f at x and y to equal to some scalar lambda times del g at x and y. And you want to take into account your constraint, which was our g of x and y equal to some c. So our c is 0 and g of x and y is y minus x squared. So here we go. fx, actually let's just utilize the gradient. So if I'm taking del f of x and y and equating it to lambda times del g of x and y, del f is going to be 2 times x plus 3 I, right? And then plus 2yj. So that gives me del f of x and y. That would equal to lambda times del g of x and y. So del g of x and y would be negative 2xi plus j. And then to solve, right, we would just equate the coefficients to the i's and then the coefficients to the j's. So we would get 2 times x plus 3 would have to equal to lambda times negative 2x, and 2y would have to equal to lambda. So if I isolate lambda in the first equation, I will have lambda is equal to negative x plus 3 over x, because the 2's will divide out. So this is going to exclude the solution of x equal to 0. Do you see that? And then this one, of course, is already isolated. Lambda is 2y. So equating those, we will have 2y is equal to negative x plus 3 over x. Isolating y, we will get negative x plus 3 over 2x. Good so far? Awesome. All right. So plugging this into our constraint equation, which remember was y is equal to, actually I'll write it as y minus x squared is 0. Then I can put in for y negative x plus 3 over 2x minus x squared is 0. And that will give us x squared is negative x plus 3 over 2x then we'd have 2x cubed is negative x minus 3, and that would give us 2x cubed plus x plus 3 is 0. And then I just solved this using technology. It turns out that you get a result of x is equal to negative 1. And now, so this here was y. So now what we'll have going on is that x is negative 1, and when we plug in x equal to negative 1 into this guy here, right? So again, dealing with y minus x squared is 0, we would get y minus negative 1 squared is 0. And so y would then be 1, which gives us a lambda, which I think ends up being 2 if you needed to find your lambda. We can put that over here. We got lambda is 2, and that was, we found x and y. Y. So Now we just need to figure out the minimum distance. So plugging this into f of x and y, let's look at what is f of negative 1 and 1. Well, that's going to be negative 1 plus 3 squared plus 1 squared. And that will end up being equal to 5. But remember, that was the square of the distance. So the minimum distance between the curve y equals x squared and the point negative 3, 0 is the square root of 5 units. Cool, cool? All right, so I just did this with one constraint. It does build to where you can use 2 constraints, but this will give you the idea of our Lagrange multipliers. And next up, we'll be starting chapter 14, multiple integration. So I hope you have a wonderful morning, afternoon, or evening whenever you are watching this show. And hey, if you like what I'm doing, please subscribe and tell all your friends. Bye.